Movement Production Strategy in Tennis, a Case Study. CETAPS Laboratory, Faculty of Sports Sciences, Rouen University, Rouen, France. Clinical Unity of Gait and Movement Analysis, CMPRE, Laboratory, Bois-Larry, France, and Movement Action and Performance Laboratory, National Institute of Sport and Physical Education, Paris, France. Introduction. Technique analysis is a method used to understand the way in which sports skills are performed. This analysis provides the basis for improved performance and enables one to inform the coaching process. Lying within this framework, the purpose of the present study was to analyze serve return strokes performed by an expert tennis player to provide a kinematics and temporal description of movement and to facilitate remediation and feedback about performance kinematics. Tennis is an activity that implies high time constraints and requires coincidence anticipation skills. In the modern tennis game, the serve and the return are important standardized movements in a world-class players that may have a significant bearing on the result of the match. The receiving players have to cope with a very high time pressure caused the high serve velocities up to 200 kilometers an hour and high degrees of uncertainty. In fact, the men's tennis game have reached a threshold in the speed of the serve where reaction times are longer than the time available to return the serve. During that time, the receiver has to get organized to defend a space of 8 meters width and play a stroke whose execution frequency spans less than 10 milliseconds. The serve return is considered as a particular shot that requires a technique of its own and differs from a normal forehand or backhand. Ground stroke. The few technical analysis, kinematics or biomechanical, that examined this task investigated the preparatory behavior of the receiver. To describe the basic movement sequence and to specify the split-step landing phase. The key factors of a successful return of serve are the timing and the movement preparation and the optimal initial position reacting on the velocity and direction of the moving ball during the serve. Technique analysis can focus on the position variance of body segments. These position variations are characterized by various spatiotemporal parameters, speed, amplitude, that constitute motion adaptation indicators with respect to different interceptive task constraints, such as the serve return shot. The degree of consistency in the movement kinematics was a source of debate when the backswing and the forward swing of the movement were separately considered. First, a predictive control strategy of the movement time, such as optimal timing hypothesis, has been used to interpret the fundamental role of the movement, initiation, timing of the success of an interceptive task. Performers were assumed to develop highly consistent motor programs needed only to predict the movement of a movement initiation in skill reproduction. Second, in a more ecologically valid setting, Botsma and Van Wieringen showed that the variability in the racket position of expert table tennis players was greater at the initiation of the movement than the movement of ball contact, implying that the expert player did not fully rely on the high consistent movement production strategy. The variability in the expert's initiation movement time was closely coupled to the variability inherent in the acceleration of the swing. This compensatory variability was considered as functional, implying a continuous visual guidance of the movement trajectories. Expert players used a funnel-like type of control, i.e. perspective control, to accommodate the movement from the initiation of the movement of the ball contact. Technique analysis can also be provided by the simulation of the human body models that allows the behavior of the modeled system to be simulated under different conditions. Then simple point mass models of a skill can be used to establish some of the basic characteristics of the technique and effect of the technique on performance. Vertical displacement of the gravity center, GC, of the human body has been presented as an excellent tool in the human movement analysis because it reflects the biomechanical performance of the whole body. Considering the serve time constrained serve return task, this technical analysis describes the relationship between the split-step landing phase and the initiation movement of the racket swing. We also hypothesize that this expert player performs its serve return strokes using a high consistent movement production strategy that was characterized by a relative consistency of lateral and vertical displacements, initiation of both its GC and its racket, whatever the type of serve executed. Methods. Experimental approach to the problem. The current study is a quantitative technique analysis to identify the key factors that affect the specific sequence of the tennis serve return movement, such as the split step landing and the backwards swing phase. This approach is based on the 3D capture and analysis of movement in a live situation. This case analysis falls within the framework of the absolute approach of expertise, because it assesses the truly exceptional individual to understand a superior performance that can be adapted as an index of expertise. Subjects. A world-class male tennis player agreed to participate in the experiment that was approved by the ethics committee of the university. Age 23 years, experience 15 years, body mass 90 kilograms and height 188 centimeters. The expert player practiced about 17 hours a week and played an average of 320 international tournament matches. His best association of tennis men professional world ranking was 7th. Procedures. An optoelectric Viken Peak 612 trademark systems with 6 cameras, V-cams operating at 200 Hz, was used to define a calibration space of 26 meters cubed, 4.65 long times 2.75 wide times 2.00 high. Thus, the full delivery player's action could be captured. This system recorded the 3D coordinates of the hemisphere infrared reflective markers attached to the receiving player and their racket to measure the amplitudes and positions of the GC estimate and their racket displacements. The lateral and vertical GC displacements were estimated from those of the first sacral vertebrae. The external marker placed on the sacrum was used to represent the total body GC and consequent the global motion of the player. A reflective marker was positioned on the head's top of the racket. The player was positioned on a tennis court in its favorite return position, i.e. 1.20 meters from the baseline and 1.05 meters from the singles sideline. After calibration procedures, the player performed serve return strokes as many deliveries as required to become familiar with the test environment. He executed double-handed backhand returns. He was instructed to perform successful either backhand or forehand strokes, depending on the serve delivered from the due side. 2 expert players executed several series of serve strokes to simulate a match play situation by combining first and second serves, ball spins, flat minimal spin on the ball, top spin, and slice side spin, and locations of the service box wide near the service sideline, into the receiver's body, and on the tee near the center service line. Variation of serves permitted one to maintain a high spatio-temporal and uncertainty constraints of the serve return sequence in the modern tennis game. Moreover, a digital video camera, Sony TRV 50Hz, Sony Corporation, Tokyo, Japan, placed behind the receiving player was synchronized with the Viken systems to record the server's actions. Thus, the duration of each serve could be measured to determine a temporal scale of all serves. Given the most often used serves of high-skilled players, we limited our analysis to the first serves that landed in the service box according to the following ball location combinations: flat and topspin serves down the tee and flat and slice serves into the wide side. Thus, 24 first serves and consequently 24 serve returns, forehand and backhand strokes were retained and analyzed. The mean velocity of serves when the ball bounced in the serve box was 183.79 plus or minus 15.25 kilometers an hour. All collected data were normalized from the serve duration that was converted into percentage of average time. It allowed us to determine the temporal trajectory of serve return. Strokes according to the duration of the serves and particularly from the impact. 3 phases of serves were considered for this normalization: preparation, hitting, execution, and follow-through. The preparatory phase begins with the elevation of the arm holding the ball, 0%, and finishes with the apex of the ball trajectory, 84%. It is successfully followed by the hitting phase that starts with the server's knee extension, 84%, and ends at the racket ball contact, 100%. The follow-through phase corresponds to the initial part of the ball trajectory, during which the racket moves across the server body with a gradual deceleration, 148%. Statistical analysis. The descriptive analysis revealed a third class of serve return, so-called reprogramming strokes. These motor tasks require a coherent spatio-temporal modification of the movement in a short time. In these cases, the player initiated a forehand stroke to successfully execute the backhand shot. See figures 1 through 3. The independent variable was the type of serve return strokes executed, forehand, backhand, depending on the type of serves, and reprogramming strokes. A set of dependent variables enabled us to characterize the temporal trajectory of the serve return initiation movement. These dependent variables concerned the racket displacement and the occurrence time, milliseconds, of the lateral racket displacement, the average time of the maximal amplitude of the lateral racket displacement, and the amplitude of the racket displacement, millimeters, determined by the difference between the maximum amplitude and the initiation, characterized by the inflection point of the trajectory of the displacement. The GC movements of the players, that occurrences time, milliseconds, of lateral and vertical GC movements, and of the maximal GC rise values, the average time, milliseconds, of the GC rise value, and the amplitude of the vertical GC motion, millimeters, determined from the maximal rise value until the following minimal value. The time of latency, milliseconds, between the onset of lateral racket displacement and the moment of maximum GC rise that was considered as the standard reference. All measures were analyzed using one-way analysis of variance, ANOVA, in which the type of serves return was considered as between participant factors, relevant assumptions pertaining to ANOVA, such as data normality, Shapiro-Wilks test, and homogeneity of variances, Levine's test, were tested. Any significant main effects were sought using the 2K honesty significant difference. Post hoc statistical significance was set at p is less than or equal to 0.05. Results. Figures 1 through 3 describe the temporal trajectory of the GC movements and racket displacements during the execution of forehand, backhand, and reprogramming serve return strokes. A significant effect was observed for the occurrence time of the lateral racket displacement. F equals 3.67, P is less than 0.05, equals 0.51. The amplitude of the racket displacement, F equals 56.72, P is less than equal to 0.0001, amplitude equals 0.92, and the time latency, F equals 10.28, P is less than 0.002. No significant effects was observed concerning the GC movements during the serve return execution. The initiation of the lateral racket displacement appeared significantly later after the serve impact for the execution of the reprogramming strokes, 360 plus or minus 24.49 milliseconds, in comparison to the forehand, 286.70 plus or minus 28.39 milliseconds, with P is less than 0.05, and backhands 285.00 plus or minus 77.09 milliseconds, with P is less than 0.05 shots. No significant differences were observed between forehand and backhand returns. The amplitude of the racket displacement is higher in forehand, 1,536.92 plus or minus 222.63 millimeters, than in backhand, 681.20 plus or minus 174.18 millimeters. P is less than 0.01, and in reprogramming, 775.42 plus or minus 222.27 millimeters strokes. No significant differences were observed between backhand and reprogramming shots. The average latency time is longer in reprogramming strokes, 297.50 plus or minus 120.93 milliseconds, than respectively in forehand, 132.50 plus or minus 45.55 milliseconds, and backhand 156.70 plus or minus 51.15 milliseconds. Serve returns. No significant differences was observed between forehand and backhand strokes. Discussion. The results of the current research showed few differences in global execution of serve returns performed by an expert player. Indeed, only one difference was observed concerning the occurrence time of the lateral racket displacement, the average latency time, and the amplitude of the racket displacement. As expected, this expert player uses a high consistent movement production strategy by initiating its different serves returns with a high degree of spatiotemporal consistency. This strategy may allow a high level of spatial and temporal accuracy in the movement. The movement initiation seems to operate a fundamental role in the success of the player's serve return strokes. This movement consistency can be supported from the theory of motor programs characterized by a set of spatiotemporal invariants. Nevertheless, in performing reprogrammed strokes, the expert showed adaptive and anticipatory skills to hit the approaching ball successfully. The skilled adaptation can be interpreted from two paradigmatic approaches. Indeed, in the lines of the motor program concept, a player must modify its racket movement independently of the initiation movement, or he may use the prospective control mechanisms enabling the regulation of movement from the initiation of the action to the moment of impact. Moreover, the lower percentage of the reprogramming strokes executed by the expert showed the relevance of this anticipation behavior. At last, concerning the relative between the split-step landing sequence with the initiation movement of the racket swing, the expert player initiated a lateral racket movement before the landing of the split step. The lateral GC movement coincided with the first foothold on the floor after the GC rise, figures 1 through 3. The expert player begins his backswing during the GC downward slope. This initiation movement, when he executed reprogramming strokes, was respectively later, after the landing of the split step, then during backhand and forehand strokes, just before the landing of the split step. In that case, ability to make accurate judgments based upon advanced visual information may be altered by different factors such as ambiguous or deceptive movements executed by servers. This case study addressed the descriptive and analytic goals of technique analysis to determine the relation between the tennis serve return technique and the successful performance. The expert player used a predictive movement production strategy specified by a high level of reproducibility and repeatability of the movement, coupled nevertheless with important adaptive performed during reprogramming strokes. Practical applications. Serve return movement production strategies and the split-step landing sequence have important implications for tennis coaches approaching. First, successful serve return strokes depend on the specific replication of individual technique that must allow the player to develop flexible but effective movement patterns to adapt his behavior to the high time constraints and thus to manage the speed-accuracy trade-off. The more difficult the serve coming at the player, the shorter the backswing movement should be. It is advisable to train the abbreviated serve return execution only through a backward rotation of the shoulders with a minimum arm rotation through the use of ground reaction force and the forward rotations of the body about its own axis, combined with the use of high velocity of the oncoming ball. Second, the timing of split-step landing sequence is crucial for the preparation for movement to a successful serve return. Although the magnitude to which a player flexes his knees is determined by various factors, player's morphology, physiology of anticipation and skill, there is a compromise between dipping too low and not dipping low enough. Moreover, to initiate a lateral racket movement around the summit of the split step can help to manage the speed accuracy trade-off. Thus, the coach has to manipulate the different constraints, player, task, and environment to facilitate the learning of or improvement of the key motion characteristics of the serve return strokes. During practice sessions, the server should vary his ball toss height and the receiver should modify his position on the court. The serve return training should not be limited to the return alone. It should encompass the server's second shot, or even better, the receiver's second shot, to verify the effectiveness of the quality of the serve return strokes. Training sessions should also include the possible perceptive learning resulting in the understanding and deciphering of the server's game style and spatio-temporal sequencing of his serve production. At last, these minor alterations to the movement production strategy and the split-step landing sequence are undetectable by coaches' eyes, who should therefore consider the use of video analysis. Acknowledgements. The authors would like to thank the French Tennis Federation of Roland Garros Institution for providing funding for this research program. They would also like to thank Atopos company Stéphane Dalberet for providing facilities. Special thanks are extended to Patrice Hegeler, the French Davis Cup coach, and Jean-Claude Machon, National Technical Direction, and Alexandre Law, Innovation Technology Director, for their support and cooperation.